In chemistry, a conjugated system is a system of connected p-orbitals with delocalized electrons in molecules with alternating single and multiple bonds, which in general may lower the overall energy of the molecule and increase stability. Lone pairs, radicals or carbenium ions may be part of the system. The compound may be cyclic, acyclic, linear or mixed. Conjugation is the overlap of one p-orbital with another across an intervening sigma bond. A conjugated system has a region of overlapping p-orbitals, bridging the adjacent single bonds. They allow a delocalization of pi electrons across all the adjacent aligned p-orbitals. The pi electrons do not belong to a single bond or atom, but rather to a group of atoms. The largest conjugated systems are found in graphene, graphite, conductive polymers, and carbon nanotubes. Mechanism. Conjugation is possible by means of alternating single and double bonds. As long as each contiguous atom in a chain has an available p-orbital, the system can be considered conjugated. For example, furan is a 5-membered ring with 2 alternating double bonds and an oxygen in position 1. Oxygen has 2 lone pairs, one of which occupies a p-orbital on that position, thereby maintaining the conjugation of that 5-membered ring. The presence of a nitrogen in the ring or groups I plus or minus to the ring like a carbonyl group, an imine group, a vinyl group, or an anion will also suffice as a source of pi orbitals to maintain conjugation. There are also other types of conjugation. Homoconjugation is an overlap of 2 I systems separated by a non-conjugating group, such as CH2. For example, the molecule CH2 equals Ca-CH2 CH equals CH2 is homoconjugated because the 2 C equals C double bonds are separated by one CH2 group. Conjugated cyclic compounds. Cyclic compounds can be partly or completely conjugated. Annulenes, completely conjugated monocyclic hydrocarbons, may be aromatic, non-aromatic or anti-aromatic. Aromatic compounds equals, conjugated, planar, cyclic compounds that follow Ha1/4 rule are aromatic and exhibit an unusual stability. The classic example benzene has a system of 6 I electrons, which forms the benzene ring along the planar O-fluorine ring with its 12 electrons. For benzene there are 2 equivalent conjugated Lewis structures, so that the true molecular state is a quantum mechanical combination of the 2 structures with 6 equivalent CC bonds which are intermediate between single and double bonds, and all of equal length and strength. Non-aromatic compounds equals, not all compounds with alternating double and single bonds are aromatic. Cyclic tetraene, for example, possesses alternating single and double bonds. The molecule typically adopts a tub conformation. Because the p-orbitals of the molecule do not align themselves well in this non-planar molecule, the electrons are not as easily shared between the carbon atoms. The molecule can be still considered conjugated, but is neither aromatic, nor anti-aromatic. Conjugated systems in pigments. Many pigments make use of conjugated electron systems to absorb visible light, giving rise to strong colors. For example, the long conjugated hydrocarbon chain in beta-carotene leads to its strong orange color. When an electron in the system absorbs a photon of light of the right wavelength, it can be promoted to a higher energy level. A simple model of the energy levels is provided by the quantum mechanical problem of a one-dimensional particle in a box of length L, representing the movement of a pi electron along a long conjugated chain of carbon atoms. In this model the lowest possible absorption energy corresponds to the energy difference between the highest occupied molecular orbital and the lowest unoccupied molecular orbital. For a chain of Nc equals C bonds or 2 N carbon atoms in the molecular ground state, there are 2 N pi electrons occupying N molecular orbitals, so that the energy gap is. Since the box length L is proportional to the number of C equals C bonds N, this means that the energy IE of a photon absorbed in the HOMO-LUMO transition is approximately proportional to 1/N. The photon wavelength I equals HCIE is then approximately proportional to N. Although this model is very approximate, I does in general increase with N for similar molecules. For example, the Homo LUMO absorption wavelengths for conjugated butadiene, hexatrene and octatetrane are 217 nanometers, 252 nanometers and 304 nanometers respectively. Many electronic transitions in conjugated I systems are from a predominantly bonding molecular orbital to a predominantly anti-bonding MO, but electrons from non-bonding lone pairs can also be promoted to a system MO, as often happens in charge transfer complexes. A HOMO to LUMO transition is made by an electron if it is allowed by the selection rules for electromagnetic transitions. Conjugated systems of fewer than 8 conjugated double bonds absorb only in the ultraviolet region and are colorless to the human eye. With every double bond added, the system absorbs photons of longer wavelength, and the compound ranges from yellow to red in color. Compounds that are blue or green typically do not rely on conjugated double bonds alone. This absorption of light in the ultraviolet to visible spectrum can be quantified using ultraviolet visible spectroscopy, and forms the basis for the entire field of photochemistry. Conjugated systems that are widely used for synthetic pigments and dyes are diazo and azo compounds and phthalocyanine compounds. Phthalocyanine compounds equals. Conjugated systems not only have low-energy excitations in the visible spectral region, but they also accept or donate electrons easily. Phthalocyanines, which, like phthalo blue and phthalo green, often contain a transition metal ion, exchange an electron with a complexed transition metal ion that easily changes its oxidation state. Pigments and dyes like these are charge transfer complexes. Porphyrins and similar compounds equals. Porphyrins have conjugated molecular ring systems that appear in many enzymes of biological systems. As a ligand, porphyrin forms numerous complexes with metallic ions like iron in hemoglobin that colors blood red. Hemoglobin transports oxygen to the cells of our bodies. Porphyrin metal complexes often have strong colors. A similar molecular structural ring unit called chlorine is similarly complexed with magnesium instead of iron when forming part of the most common forms of chlorophyll molecules, giving them a green color. Another similar macrocycle unit is corin, which complexes with cobalt when forming part of cobalamin molecules, constituting vitamin B12, which is intensely red. The corin unit has 6 conjugated double bonds but is not conjugated all the way around its macrocycle ring. Chromophores conjugated systems form the basis of chromophores, which are light-absorbing parts of a molecule that can cause a compound to be colored. Such chromophores are often present in various organic compounds and sometimes present in polymers that are colored or glow in the dark. Chromophores often consist of a series of conjugated bonds and or ring systems, commonly aromatic, which can include Ca-C, C=C, C=O, or N=N bonds. Conjugated chromophores are found in many organic compounds including azo dyes, compounds in fruits and vegetables, photoreceptors of the eye, and some pharmaceutical compounds such as the following. See also, resonance, hyperconjugation, cross-conjugation, polyane, conjugated microporous polymer, list of conjugated polymers. References and notes.